Okay. Hello, everyone. So today we're going to have our final lecture, and the focus is going to be on SQL. So we talked about relational algebra, and we looked at a couple of interesting queries that we can express in relational algebra. And now moving forward to the SQL. We're going to use the same schema that we did for the relational algebra. So we have the Sailor and the reserve table. So these are two instances of the Sailor table and with our reservation. So all our queries is going to be based on this simple schema. The structure or the syntax of basic SQL query is you have a select clause, you have a from clause, and you have a where clause. Select clause are the set of attribute that you want to pick. In a sense, select clause maps to the projection of the relational algebra. The from clause is the list of the relation. The where clause are the condition that we are imposing. So kind of the where clause, in a sense, maps to the selection of relational algebra. The select of SQL maps to the projection of relational algebra. So the unfortunate mismatch of naming, but that's the standard for many years now, for several decades. And in this qualification or this condition, it could be any arbitrary Boolean expression, and it could be an attribute, for example, age, an operator greater than, equal, not equal, attribute operator a constant, age 30, or you could have attribute operator another attribute. For example, the SID of the Sailor table to be equal to the SID of the reserve table, sort of the building block of constructing joins. So you can express those conditions using attribute operator constant or attribute operator another attribute. And then this condition, this qualification can be kind of become expanded and more expressive. And we'll look at a couple of examples later today. But that's just a basic syntax. And I think we probably may be already familiar with it, but I think it's important to know this, and because it's kind of universal. Whenever you want to use any database, it kind of is expected, at least we know the basic syntax of the SQL query. And if you remember in the relational algebra, by default, or the only way is that we have set. So all the input and output of executing a relational algebra query is always going to be set. SQL has a different semantics. It's back, and that's just it's a choice. So the default is a back semantics. So if you want to turn it into a set, we need to use the word distinct. So when we say select distinct, this eliminates any duplicate rows in the resulting relation. Again, the input is a relation, the output is a relation. So that still applies to SQL as well too. Any question on the basic syntax? And as we talked about this before, the conceptual evaluation is that we can say that we compute a cross product among the relation list, assuming there's more than one relation, there's join involved. Then we discard any tuple that doesn't meet that qualification, and that's the way exactly what we did for the when we did join in the relational algebra. And then we delete any attributes that are not in the target list or in that projection or in SQL in our select clause. And then we can either apply whether we want to duplicate, remove duplicate, or we want to keep duplicate. Distinct will of course remove it. So again, conceptual evaluation of a SQL query again can be mapped to the use of cross product, which kind of stress it again, it's powerful enough that allows us to design this conceptual evaluation. Of course, as we said it last time too, is that Conceptually, it makes sense. Semantically, it makes sense. But efficiency-wise, it's probably the least effective way of executing query in this form. And another example of this conceptual evaluation, so now let's look at the first syntax, is that select sailor name, the S name, from the table sailor, renaming it S, and from the reserve table, renaming it R as a shorthand, where the SID of the sailor is equal the SID of the reserve, the R, and the BID is equal 103. So basically returning the name of all sailor who have reserved a boat with the ID of 103. And we looked at this in the relational algebra, the same query as well too. So one way to do this is that do a cross product of S1 and R1 and all combinations. So Dustin is matched with 22, Dustin matches 58, Dustin matched with 22, Dustin matches 58, Luber is matched with everything, and then Rusty matched with everything. And the one that satisfies the first qualification or first condition of SID is equal RID is, for example, here SID is equal the SID of the reserve. And what else? Here, the first one as well too. The SID is equal the SID of the reserve. And then there's a second condition. So first, we're going to filter out anything that is not equal. Their SIDs are not equal, so we'll filter out this row, filter out this one, filter out this row, and filter out this row as well. And what remains is the first and the last row. But then there's also a second qualification or second condition that enforces that the the boat ID to be 103. Of course, this does not meet the first row, and the only one that satisfies the second condition is the last row. So we can do a cross product, eliminate all unqualified rows, and what it would remain is the one qualified row, which is the last one. And that's a conceptual evaluation. Of course, there would be a lot more efficient way of doing it. For example, if we had an index on BID, we could have just looked up all the SID associated to both 103, and for those, we would, for example, then get their name. So if we had an index, we could do this much more efficiently. And there's many other ways of doing this evaluation. But conceptually, this is what it means. And conceptually, this is, well, not this conceptually, and this is the syntax of how to express this simple query in SQL. Any question? Okay, so let's move on. And again, as mentioned, we can name relations. So instead of just calling it sailor and reserve and say sailor's SID, we could give it a shorthand name, so which is useful, good practice, more readable query. Also, it becomes essential if you're doing a self join. If you were joining the sailor table with sailor table itself, if we're doing a self join, then in order to distinguish between the two sailor table, then we would definitely need to use these naming convention. More matter of a syntax. A bit more syntax is that in our select clause, we could say, for example, sailor age, or we could define a new attribute into our schema to be selected. We could define this new attribute at age1, which is equal the sailor age minus 5. Or we could say we want a third attribute 2 times of the sailor age, and we call that attribute age2. So 2 different ways of defining new attribute added to the relation resulting from the SQL queries. The other syntactical thing is that the where clause, we could also deal with string and wildcard. So for example, we say name, it's like start with a B. It could be any one character, the ampersand, it could be, or the percentage sign, it could be 0 or more of any character, and it ends with B. So we could kind of start having regular expression embedded in our SQL as well too. Again, just matter of syntax, extending the functionality in order to write more expressive queries, but easier. Any questions? That's just the text of what I described. So now let's kind of look at writing some more interesting queries. And some of them is a repeat of what we did, but kind of see how they look like in SQL. So this is one query we did last time. Find the set of all sailors who reserved a red boat or a green boat. So let's see if this query does answer that. Select all the sailor. And since we want to be able to choose the color of the boat, so we need the sailor table, we need the boat table, and we also need the reserve table with the reserve relation. And so we join the sailor table with the reserve table, so that's a one join. And then we join the reserve table with the boat table. So kind of extending it from sailor is extended by reserve. Reserve is extended by the boat information. Now, if the boat color is green or red, that entire row gets selected. And from that entire row, we pick the SID, and so that would be the SID of a sailor who either had reserved a red or a green boat. Any question on that? Does that make sense? And what happens if we replace the or by an and? Of course, if we do that replacement, we're not going to have a single boat of having two different colors. So we're not going to get return anything. And so that's one way of expressing it. And same thing with relational algebra, but more even prominently in SQL, because there are additional features have been added to the language for ease of use, not to necessarily extend the expressiveness, but often for ease of use. So this is another way of expressing the same query. So instead of as part of the where clause, the qualification, we search whether it's red or green, we could write one query that find all the sailor who have reserved the red boat, write another query, find all the sailor who have reserved the green boat, and then union the two in order to find all the sailors who have reserved either a red or a green. So that's another way of expressing the exact same query. Now the question is, which one do you think would be more efficient to execute? Of course, if the optimizer is clever enough, it can rewrite either one to a more efficient form. But if you were to just follow the exact what is written here, which one do you think would be a more efficient execution?
The first one.
And why is that?
Because you're not selecting it again, you're not doing all the select from where all again.
Yeah, so exactly, because here you're doing this join, or you can even conceptualize it with that cross product, you're doing it once. But here you're doing it once for the red, and then you redo everything again for green. So of course it's going to be much more costlier. You may essentially double do the double amount of the work. There's also another operation that can be used, is that similar to union, you could say except. So giving me all the sailors, for example, let's see what happens here. Give me all the sailors who reserve the red boat, except all the sailors who have reserved the green boat. What would you think this would result if I have the word except? It's kind of a minus set difference. What would that resulting query be if this union was changed to except?
Well, then that only chooses the red one.
Chooses the red one, conditioned that. So that's the first part. What's the second part?
But then if the second part is the color is green, to accept the green ones, I mean, when you select the red one, you wouldn't include the green ones already, right?
Yes, but the except or the union is applied on the output. This gives a list of SID. This gives a list of SID. The union would have create a union of these two lists, except would have
taken
this
out
set minus that set. So what would that be then? If you were to say it in English, what would this query would return? If somebody had reserved both red and green, would that person show up in the final result?
No.
So then
it would just be the list of sailors that who've only reserved the red votes.
So perhaps a bit more precisely is that all the sailors who have reserved a red boat but haven't reserved a green boat, because it could be other colors too. So as long as they've reserved the red boat and they haven't reserved any green boat, then it's a qualifying sailor. Does that make sense? Okay. So now let's kind of make the example perhaps a little bit more interesting. Find the sets of sailors who have reserved a red and a green boat now. So how would we express this?
Select SID from sailor where this boat or boat is equal to red and green, or boat is equal to green, or in. I guess you can say in. Something like that.
Well, so yes, but we're kind of now gonna get into the challenge of saying that if the boat is green and red, it's not that the single boat is green and red, it's that they have two different reservations. One of them is with the green boat, one of them is with the red boat. So that's where that challenge is. But there is also a simpler way, because SQL gives us this operation called the intersect. And so we can just get all the red, get all the green, and intersect their set. So that's a sort of a simplification. So using the intersect, relational algebra gives us the minimum that we need to define our expressiveness. SQL is not so much about the minimality of giving us the minimum. It's giving us enough functionality or enough operator to allow us to write queries simpler. So that's kind of also one difference. And each vendor would actually, in addition to the standard SQL that most vendors support, each vendor also have their own specific features to, again, allow customers to write queries more simpler. In fact, if you have a big account and if you're a sort of a big customer, they would actually create a unique build or a unique version of their database, whether it's Oracle or if it's DB2, for example, for that particular customer. A particular build that the feature that exists in that that version of the database may not even exist in regular version that is available. Anybody, for example, can purchase. And so again, there's a lot. Each vendor has added a lot more unique functionality. But intersect is a standard as part of the SQL, and it really simplifies that. Get a list of red, get a list of green, intersected under SID, and if it appears in both lists, then it's going to be part of the intersect and part of the answer. But what about this one? And that's kind of a little bit closer to what you were mentioning, actually. So what's happening in this top query? Is this a valid one? Does that make sense? There's 1, 2, 3, 4, 5 relations that are being joined. And the relation both is being essentially self-joined, and so is the reserve. So what happens? So kind of see my hand is that we start with the sailor, we join it with the reserve. So for every sailor we expand it with the reserve, we expand it with the boat. So going that direction, we get a sailor, we get a reservation of the sailor, and we get the information about the boat of that reservation. And now imagine we extended this from the other side as well. The same sailor, we again join it with the reservation, extend it with the reservation, and then extend it with the boat information. So essentially we're getting two reservation entry aligned. And since there are two different reservation entry for the same sailor, and it could be, for example, if this sailor had two reservations, it could be that one of them is a red boat, one of them is a green boat. Or it could be both of them are green boat. If they're both green boat, would not be qualified. But if they were both, but if one was red, one was green, then that would be a qualifying. So it requires multiple self-join and it requires number of joins, but that's another valid way of finding that. But we wouldn't be able to just do it with a single join of the reserve, because otherwise we would be kind of saying if the same boat is both green and red. Here we're actually taking two reservation entry, attaching it together, and we say one of these reservation is a green boat, one of them is red, then it's qualified. Does that make sense?
But in this scenario, doesn't it have to be the first reservation has to be the red boat, and then the second reservation has to be the green boat, or can it be either or, like the reversed way?
Yeah, so that's a very good question. But since it's a self-join, it's every sailor is going to think of that cross product. Every sailor is going to be matched with every reserve and every boat. And it doesn't really matter what order it is, because every sailor is going to be matched with all of them. And it's going to be matched with all of them twice. So all combinations, if you think of the cross product, all possible combinations have been considered. So since all pairwise combinations are considered, that means there will be a case that the red is first, then is green, and it's also a case would be the green first, then is red. So all of those combinations are explored. And we pick any of them that have in the same row, once you attach them, has both the red and the green. Again, remember, cross product, again, not worrying about the efficiency of how to do this. The cross product looked at all possible combination, took one row from this relation, just join it with everything in the other relation. And so now we're taking one row in that relation, join it with everything with the reserve, and then again, so the resulting of that, we join it now with everything in reserve again. So the relation, every time we do a join, it gets bigger and bigger and bigger. So assume you had a single sailor and you had 10 reservation for that sailor. Once we get the sailor and join it with the reserve once, the resulting cross product would have 10 entries. Now, if you join it cross producted once more with the reserve table again, now we will have 100 entries because it has all the combinations. Because for each of that 10 cross product that came out of the sailor and the reserve, for each of them, it's going to get now cross product with the reserve table again. So now we would have 100. So every time we do these, essentially these cross product, again, we are looking at our combination. We're doing all pairwise comparison, or all pairwise combinations is included and squared. You have to think about it a little bit for it to set up, because it's not, it's a bit counterintuitive at first. And this is essential to understand this, because this is the power of essentially doing self-join, joining the relation with itself. And it's really powerful concept that it's used extensively. It's usually turn out to be many queries can be leveraged this self-join, and they're very useful in practice. Any more questions on this self-join? Okay. So you also have nested queries. Again, they get interesting. And again, these SQL queries, I mean, there are people who their day job is to write SQL queries. And sometimes these SQL queries could be, as I had mentioned before, could be pages and pages long. I mean, they're fun to write and they're complicated, and it's like solving a puzzle. And again, for reporting or application, really often relies on these complicated SQL queries. So nested query, look at an example. Find the name of the sailor. There is a subquery here. Get the list of all sailor who have reserved a boat 103. Now, finding the name of all the sailors whose SID belongs in this set or in this bag. And what is in this set is the name of this SID of all the sailor with 103. So if this SID, so you can imagine that I am going at the top level query, I'm going over every single record, and I ask whether the SID of this record that I'm looking at appears in this set. And the way that I compute this set is that I simply run this query once, get the SID of all the reservation of boat 103, and then I can imagine putting inside this bracket that list of all SID, and then as I'm going through my relation, I check the SID of the current row. If it's in that list, then it's qualified. If it's not in that list, then it's not qualified. Does that make sense? Okay. And you can also make it a little bit more interesting to say not in. So give me, then it would be list of all sailor who haven't reserved both 1 or 3. So that could be another use case of it. So, and again, this is referred to as nested queries. In fact, from your this sailor itself, we could have a nested query here. Instead of have an actual table, this could also be replaced with another query, and we know the query returns a relation, so essentially will be another relation, another usage of nested query. Any question on this? And again, I'm going to incrementally build on it, so if you have any question, please ask. Okay, so nested queries now with correlations. So find the names of the sailor who have reserved both 1 or 3. Let's look at the same query. And here is another way. And this time it's another operation called exists. And let's kind of go over this query. Give me all the sailors' name taken from the sailor table for that particular sailor. So imagine I'm going over every records of the sailor, and for every sailor record that I encounter, then I'm going to run this query. I'm going to select from the reserve table those reservations with the both 1 or 3, and also those reservations who the sailor who reserved it matches the current record of the sailor that I'm encountering. And if this subquery or this nested query returns any result, the exist, meaning something exists in this bracket, is evaluated to true. And if this is evaluated to true, the qualification or that condition is satisfied. Therefore, the name of that sailor will be selected. Then I go to the next record, then the next record, then the next record. And so that's the way that I would execute this query. Does that make sense? Any question on that? So do you think, would this be more efficient compared to what we did in the previous slide using the in operation? So comparing using this in operation, find the name of the sailors or their SID lies in this relation, in the subquery, versus using the exist operation. Which one do you think would be more efficient to execute? And of course, why?
Would it be the same?
Okay. No, one of them is better. Again, think about the way I said the evaluation. How many times this subquery needs to be reevaluated in the first case? How many times the subquery needs to be reevaluated in the second case? So going back here, how many times do you need to reevaluate this subquery? The only thing that we need to do is just this query is fixed, is not dynamic. It's just one thing. Give me all the SID of whoever booked both 1 or 3. It's a static query. It needs to be evaluated once. And once I have the result, then I can always cross-reference it. But here, this subquery, it actually, the query itself changes depending on the row that I'm looking at. First, if it's a sailor 1, this is going to be replaced with 1. So this is going to be a new query. When it's 2, this is going to be yet a new query because this is going to be the value 2. When I'm looking at the third record, let's say the third sailor, this subquery needs to be reevaluated because now this is for sailor 3. So as you can imagine, as I'm going down and examining every record in the sailor, I have to reevaluate the subquery every single time, which is why this is correlated to the top level query, because it's referencing a field or a variable or a column one level higher. The previous example, it wasn't the case. This subquery was independent. There's nothing in this sailor relation that are being accessed here. It's just a self-contained query which only needs to be run once. Doesn't matter how many times you run it, always going to get the same answer, so you run it once. But versus when you have that correlation, is depending on, for every record, basically for every record in this table, in the sailor table, a unique query needs to be run. So in general, this tend to be much more expensive. Of course, maybe if you have an index on, if you had an index on SID and a bit ID, each evaluation of this could have been one index lookup. So maybe it wouldn't be super expensive. And in fact, if this list is too long, if I had done it this way, if this list is really large, is let's say millions of records, then I have to kind of manually do a search in this huge list. And this query could now become more effective because for every sailor that I'm looking at, I could just look up one index as opposed to go over this long list that I have generated. So there are scenarios that this could potentially be more effective. And also, again, it helps us to write more complicated query. It gives us another tool for writing complicated query in a simpler form. There is usage for it. There are some cases that really simplifies expressing that query. But in general, correlated nested query with correlation or correlated nested queries tend to be more expensive because this inner query needs to be rerun repeatedly given the input parameter of the higher level query, top level in the hierarchy. Okay, we talked about why it needs to be reevaluated. So any question on this? So again, exist. If the result of this is non-empty, the exist is evaluated true. We can also say not exist, or we can say not in. And if we had said not exist, then only that sailor would have been selected if this didn't return anything. So if I had said non-exist, I would have get the name of the sailor who have not reserved the boat 1 or 3. Again, it is powerful. I mean, it's useful. It really simplifies the expression. At the end of the day, most of this cross product. So surely the relational algebra that you have to write, it's not going to be fun writing, probably would be very tedious, but you just need cross product and the selection. And that's really how powerful those 5 relational algebra that we talked about, how powerful they are. Okay, so again, these combinations exist, not in, not exist, unique. There's more. You can say, for example, let's look at an example. Give me the sailor whose rating is larger than any other one with the name, particular name, or larger than anyone if you had all, larger than everyone, or larger than at least one. So again, this is really simplifies expressing certain reporting. I mean, again, depending on the query that you want to write. So additional operation to simplify writing our queries. Any question? Again, this operator can be any of these. Okay, let's come back to our favorite topic, division, and let's see how that's going to look like in SQL. The good way of doing this is to kind of sit down and try to write it down yourself. And I think even after today, once you've seen it, I think if you wait 24 hours, there's a good chance you forgot. You'll forget because it's a bit counterintuitive. So then again, try to see if you can write it down by thinking about it. Of course, there is a hint that you can sort of experiment, see if you can remember it. But and it's difficult to kind of do it without the blackboard. So, but let's give it a shot, see how that works on Zoom. Okay, find all sailors who reserved all boats. I think we did well for the relational algebra one. For the SQL one, it's a little bit, there's actually many different ways of doing it. We're gonna look at two, one is harder, one is simpler. So, and you're going to first try to do it without using the except operator, because that will really simplify it, as we're going to see next. So I am going to select a set of sailor for which some condition doesn't hold, or for which no result is being returned. Okay. And then inside that, I am going to select all boats. And for every boat, I want to make sure for every boat, I want to make sure it doesn't exist a reservation for which, for that particular boat and for that particular sailor, there is no such a reservation. And if there are no boats that satisfy this, then that sailor is selected. Okay, let's have to do this a couple of times to get a good understanding. So what happens in this lower one, in this is again a nested query, 2 level deep. What happens in this, the most inner one, is that I get the reservation given the boat above, given the sailor above. So for every sailor, I am going to enumerate over all the boats. So now for every combination of a sailor and a boat, I see if there's a reservation. I see if there's for every combination of a sailor and a boat, I check if there's a reservation. If there is a reservation, the not exist condition, if there is a reservation, the not exist condition would, what happened to it? If there is a reservation, what happens to this non-exist condition? If there is a reservation, that means that both would not be qualified because there's a reservation. This non-exist will fail, and that boat will be selected if there is a reservation. So I kind of need a little bit kind of feedback on, so see where everybody is, so I can make sure that I can walk through you to it. So what happens in this lower one is that I see if there is a reservation for a particular boat and a particular sailor, okay? And if there's no such a thing, that boat will not be selected. If there is a reservation, that boat will not be selected. So that means if for every boat there is a reservation, no boat will be selected for that particular sailor. That means that sailor have reserved every single boat. So one more time. This, for every sailor, I take one sailor at a time. Let's say I have only one sailor. I take my one sailor, I go over every boat in my boat table, and for every boat, I ask whether there is a reservation for this boat by my sailor, by my only one sailor. If the answer is yes, then the non-exist clause will not be satisfied and that boat will not be selected. So now, if for every single boat there is a reservation, no boat will be selected as part of this select clause. That means if no boat is selected, this non-exist condition satisfies to true, therefore that sailor has reserved every single boat. Even if there was one boat that sailor didn't reserve, so there was one boat that sailor hadn't reserved, then there wouldn't have been a reservation entry here. So then that boat would have been selected as a result of this query. And if this query is non-empty, the non-exist condition won't hold and that sailor wouldn't be selected.
So, quick question. So it will only ever return something only if like all boats are reserved by that particular sailor?
Exactly. So that's the division operation that we looked at last time in the relational algebra. So you want to find the sailors, find the name of all sailors who have reserved every single boat.
Okay, thank you.
So there is a sailor such that there is no boat without a reservation. So as long as for every single boat there is a reservation, this whole thing will be empty. And if that whole thing is empty, then that sailor is selected. Another way of doing it, select all sailors where the following condition doesn't exist. Let's write it, and then we'll go over it. Select all boats, and then remove from it any boat that is reserved by that sailor. Select all boats, remove any boat that was selected by that particular sailor. So this is a correlated query. This is a correlated query correlated to that one. This one is not a correlated query because doesn't have any parameter that is reference the top level query. So, but for every sailor, we will have to look at this subquery. We get the list of all boats. We get the list of all reservation. we subtract the list of boat minus the list of reservation. If every single boat is reserved, this subtraction results in 0. The non-exist becomes true, and that sailor becomes qualified. Even if there is a single boat that sailor did not reserve, then this could be 9 boats, and then if that reserve only 9 boats, then 1 boat remains, the non-exist will fail, that sailor will not be qualified. So that's a much sort of simpler way now using the except operation to do this. I mean, here we're using only not exist, we're not using except. When we did with relational algebra, we didn't have the luxury of any of we didn't have the luxury of non-exist or any of that. We did it entirely based on the cross product and just the set difference, which is kind of similar as except. Any questions on these two different example of doing the division in SQL? And you may think of other ways, more creative ways of doing it. Okay. So more syntax, more interesting thing that can be done. For example, we can count rows, we can count distinct rows, we can sum up the rows, we can average the rows, we can find the max, we can find the min. So again, these are extension. I mean, of course, the relational algebra couldn't do this. We cannot express the count in those 5 operations. So these are just some additional sort of statistics, something that is needed to be extended. I mean, we can do with all the cross product, and that gives us a lot of functionality, but like doing any statistics is just simply not possible. So that needs to be, these additional operators need to be added. For example, we can say, so this is counting all the rows. So when we say count star, that means basically count all the rows in a sailor table, and this returns the number of records in sailors. This is finding the average age of a sailor with a rating 10. So the count, all of these will produce a single value. So a set goes in, one value comes out. So the set of all relations gets counted here. Here we are extracting all the sailor with a rating 10, and among those we find the average age. One value is returned by this query. Here we are counting a distinct number of rating for any sailor who has name Bob. And I mean, Bob, the name is not a unique key. So there could be many sailor who have name Bob, and they may have different ratings, and they may have duplicate rating. They could be Bob X, rating 1, Bob Y, rating 2, and there could be different rating. So here is counting the distinct number of rating among sailor named Bob. This is finding the average distinct age of sailor of rating 10. So if there are many sailors of rating 10 of age 100, probably too much of 100, but if there are many sailors of age 75, then we're only going to consider the age 75 once. So if you have 101 sailor, 100 of them are age 75, and only one of them age 20, when we want to do the average, we just do the average based on those two numbers, number 20 and 75. If we didn't have the distinct, we would have 175 and 120. So the average would be very different. And they can also, another sort of thing that is supported, you can select S from some table where the column inside of it could be another clause. So these are kind of addition things that are not supported by our basic relational algebra. Is to really finding statistics on top of the returned results. Any question on these extensions? Okay. So find the name and age of the oldest sailor. So does that make sense? Select name. Is this do you think this would be a valid statement? What would this return, this query? This essentially is that it's going to get the name of the sailor and it's going to just add the maximum age of any sailor. So it's not, these two are not really related to one another. And in fact, it's not even a, the database will flag this as an invalid query. It's a malformed query. So one way of finding the name and the age of the oldest sailor is that I can say, give me the name and the age of the sailor, who's the age of that sailor that I'm looking at right now. It's equal the maximum age in the sailor table, because the maximum, as I said, these sort of statistical kind of operation is return a single result. And so I can max it on the age of the entire table. So maybe the maximum age is 87. So I get 87. And now I can look at every record, every sailor in my sailor table. If the age of that sailor is equal 87, then it's qualified. If it doesn't look, if it's not equal 87, it's not qualified. So this is a valid query. And some may allow you to kind of write it in this form. They're kind of essentially the same. So I can select it where first I can write this clause and then say this clause is equal s.age. This is a valid SQL standard. This is not, but it is supported by some vendors. Probably is supported by most vendors. Any questions? Okay. So now there's another one, is that to create groups. So far these aggregation operators that we've done was on all tuples or on all qualifying tuples. But now maybe want to do something more expressive. Find the age of the youngest sailor for each rating. So it's no longer I'm asking for the youngest or the oldest sailor. I wanted to do that for every rating group individually. And I don't know what are the different rating groups individually during the runtime, because one instance of the table could have 5 rating groups, another one could have 20. So that's something that I wouldn't know a priori. So, and then the syntax for this, I could run this query, assuming I know it a priori. For example, I could have loop, let's say if I knew there were only 10 ratings, then I could write 10 queries, 1 to 10. And for each, I say, give me the minimum age for rating 1. Give me the minimum age for rating 2. Give me minimum age for rating 3. But I need this additional looping mechanism, for example, in my application, or I need to manually write these 10 queries. And if tomorrow there's more, then I have to kind of increase the number of ratings. And potentially have to keep issuing more and more queries. So what the group by does is I can sort of, this is the syntax. So this is the select. It gives me a group by feature, so I can group by rating. And then it's also having clause to also add a qualification for those groups in the same way that we add qualification for the records. So we can filter out records, we can construct groups, and we can also filter out an entire group. And then I could also then compute an aggregation on each individual group, for example, their age. Let's look at an example. Actually, before looking at an example, any question on just the syntax? I'm going to skip the text in the interest of the time and just look at an example. I think it would clarify it. Okay, so let's look at a couple of examples. All right, so the question that I want to answer, find the age of the youngest sailor with the age greater than 18 for each rating with at least 2 such sailors. So I want to find the age of the youngest sailor with the youngest sailor whose age is more than 18 within the age 18 group, and within that rating group we wanted to have at least 2 such sailors. So let's look at this query. Is that I want to find the age of the youngest sailor of sailors greater than 18. So that's essentially becomes a filtering condition. And I am going to also group by rating. So I'm going to group all my records into different rating 1, rating 2, rating 3, rating 4, and so forth. And I want to make sure each rating have at least 2 records or 2 sailor among them. And what I'm going to return is the rating of that group and the minimum age in that group. So, for example, let's look at the result. So this is our input relation. Let's look at the result. Let's say Y3 was selected. That will help us. So rating 3. So we have 3 sailors who have rating 3, okay? All of them are greater than 18, okay? So when I did the group by on rating 3, all 3 were qualified. And so there were 3 of them. So since that this particular rating had 3 records in it, the having clause, so this is filter out anything that had below 18. After everything had below 18, within that rating group, if that rating group had more than 3 members, then that group becomes a valid group. And within that valid group, I am going to extract the minimum age. So the minimum age in this is 25.5. Let's look at rating 10. So rating 10, if I were to apply the filtering condition, I'm going to first apply the filtering condition. Then there's only one of them that is going to qualify greater than 18. So this will be a qualifying record. So the group, the rating 10 group will only have 1 member, will not satisfy the having clause because it says that group has to have at least 2 members or more. So that's why number 10, rating 10 does not apply here. Let's look at 8. 8, both greater than 18. So both of them will appear in group 8. And since there's 2 of them, the count is also, the having is also applied, and the age is 25.5, and that's why it's in the results set. Let's look at 7. Again, 7, there are 2 of them, both of them larger than 18. And since there's at least 2 of them, it's qualified. If you look at 9, well, 9 is only 1 of them. So even though it's greater than 18, the group of rating of 9 is only 1, doesn't satisfy the having clause. 9 is not selected. And for the same reason, 1 is also not selected because there's only 1 of them. Any question? Again, this is allow us to chop the data into groups, and then it allows us to also say some condition about each group, and then it allows us to find some aggregation within each group. So as opposed to just doing some form of an aggregation in the entire table, we can chop it into different groups. So for example, I want to find the smallest or the youngest student in every class offered, in every computer science class. So I don't want to just find the youngest student in computer science. I want to group by student by the course, and within each group, I want to find the youngest student. And I also want to make sure that I only want to look at classes that have at least 50 students. So the group by condition allows me to group by student by the course, and then the having clause allows me whether this is a valid group or not. And the valid group for me now is that it has to have at least 50 people enrolled in that class. If it's below 15, I'm not interested in, because perhaps it's not statistically significant. And then within each group, then perhaps I want to find the minimum age, or I want to find the average grade in that course. And then maybe I want to have additional filtering condition on the actual record, saying that I don't want it to consider any students who have received the grade F. Those students I want to kind of not include it in my statistics. I don't want them to bring down the average. I want to just look at the student who completed the course successfully and actually had a passing grade. And I want to only find the average among the passing grade. So then I create a group for each course. I filter out using the where clause any student that was who didn't had a passing grade. And I also have a having clause making sure that each classes was at least size of 50 or more. Then I'm going to say, now give me the average of the grade within those groups. Any questions? So I think this is probably the most important last piece that I want to say in this lecture. So I think this is a good point to stop. And again, it was wonderful to have you all. It was a pleasure, and I certainly enjoyed it very much. And I've been looking forward to your presentation, your final presentation tomorrow. And I will be around if you have any questions. And have a wonderful day. Thank you.